Okay. James not here yet, so just a few more seconds. Okay, so I think we're ready. So the last speaker today is Bill Casselman from University of British Columbia, and he will talk about Schwartz functions and L functions. Please, Bill.
Okay. Yes, I'm sorry that I'm not attending in person, but it's very difficult for me to travel these days. So what I'm going to talk about is something which seems to have almost no overlap with anything anybody else is talking about, although there are a few hints that maybe something is possible. About the same time that Langlands proposed his program, which we now call Beyond Endoscopy, there were some suggestions by Braverman and Kazdan, which extended the basic idea of Godemont and Jacquet to at least local analysis involving L functions on certain reductive groups. They proposed that instead of the Godemont and Jacquet used the action of GLN on the matrix algebra. For example, locally, the p-adic groups on the local matrix algebras, and extended Tate's techniques in order to prove a functional equation for a global L function attached to the standard representation of the L group GLN. Then Braverman and Kazdan conjectured the existence of a Schwartz space on a monoid, an algebraic monoid, first invented, I think, by Winberg. And this would generalize the Schwartz space of the local matrix algebra. And one of the functions in this space is what they called a basic function, the inverse with respect to a Satake transform of the L function that you're interested in. For Godemont and Jacquet, this just came down to the characteristic function of the integral points on the matrix algebra. And this played a role both locally and globally, analogous to Tate's local zeta functions. Braverman and Kazdan were rather vague as to what their Schwartz space actually was. In particular, they didn't describe the basic function very carefully, except by its definition. A little bit later, Laforgue defined a Schwartz space in terms of a Plancherel formula, where the Plancherel measure involved the L function. But it was very, very difficult to deduce useful properties from Laforgue's definition. And Go and various co-authors since have proved a number of results regarding the propositions of Braverman and Kazdan, but remarkably enough, they don't actually tell you what the basic function is nor exactly what their Schwartz space is. So I'm not sure exactly what other people know or don't know, but it seems that there's a lot of open questions about that. So in this talk, I'll actually give you an explicit formula for the basic function associated to any irreducible representation, any finite dimensional representation of GL2C, and derive from that a characterization of the Schwartz space. These techniques will probably, well, I don't know, extending these to higher groups of higher rank is extremely complicated, as I'll demonstrate later. This space, so the Schwartz space becomes a space of compactly supported functions of a certain sheaf on a certain space in which G cross Gx, just as on the matrix algebra. But what's unusual is that the spaces I introduce are very different from the monoid proposed by Braverman and Kazdan, and which Ngo and his colleagues have all worked. They're spherical spaces which in some sense cover the Winberg monoid. But the relation between what I know and what I'm going to show you and older results is not quite clear to me. These Schwartz spaces are quite new and quite natural. So the basic function, as we'll see, I'll be able to show you a lot of examples. I'll show just one or two examples. And even then you'll see that they turn out to be somewhat exotic. The case of Tamagawa's characteristic function of the matrix and integer matrices doesn't really give you any hint of what's involved. And it's not clear how you can use these exotic functions in subsequent work. It's really a big mystery to me, but the results are interesting enough that it's promising for something. There are many unopened answered questions, some very serious. Among the most serious are what happens for groups of higher rank? Are there global applications? For example, can you get in any sense of Poisson summation formula? And more interesting and maybe answerable in the near future, what about GLNR, GL2R? As I say, I have no idea really at the moment how to relate this to work of Van Gogh and various people. I'll say something about this later. My notation is just a standard notation. Oops. Sorry, excuse me. Except for one thing, I require that the center of the group G, and this is true in all of Braverman Kazan's work, the center of the group G hat, the L group, be identified with the multiplicative group of the complex numbers. And dual to this, the group G has to have a homomorphism onto G star, onto K star. So for example, the standard example is just GLN, and the map that you need is the determinant map. And the dual of GLN is, of course, GLNC, and that center is isomorphic to C star, multiplicative group of C. The definition of the basic function involves a Satake transform. The Satake transform is an isomorphism of the Hecke algebra with the ring of conjugate invariant affine functions on the L group. The spectrum is a set of conjugacy classes in the L group. And so each unramified representation corresponds to a conjugacy class called its Satake parameter by most people, but protested by Langlands, who calls it the Frobenius-Hecke class. The only group for which we'll need details about the Satake transform in this talk is GL2. And this thing now, the standard conjugate invariant functions on the L group are just the characters of the irreducible representations. And so I give a name to that. I call it chi sub m. And that's the character of the symmetric algebra acting, the symmetric space of degree m of the standard representation on C2. And then the Satake transform is easy to describe in those terms. I let f sub mn be the characteristic function of the double coset k with some matrix. This is the pi mn is the diagonal matrix with omega m, pi m in the upper left-hand corner and pi omega n down low. And then the Satake transform takes this, as you've probably all seen at one point or another, the map is very easily described. It takes the determinant of n, which is a function on the group, into the, it takes fm, if m equals n, it just takes the characteristic function of the k itself into the product, into the determinant of n, and has the other formulas I described there. So for us, the most important thing to remember is the theorem which comes out of this, that for GL2, the inverse of the Satake transform takes some normalizing factors times the characteristic, the character of the irreducible representation parameterized by m minus n into a sum of characteristic functions of a very simple sort. And that's all we'll need. For groups of higher rank, it's much more complicated. There's a Kazan-Lustig polynomial which enters into it and makes things rather pessimistic, I would say. So what is the basic function? Well, for the moment, don't work just with GL2, but for the moment, allow G to be an arbitrary reductive group, assign something like the determinant map. If pi is an unramified representation of G and sigma is an irreducible finite dimensional representation of the L group, the associated L function is, as I wrote down below there. So that's very simple. It's a function of S. For a fixed S, this is clearly it's clearly conjugate invariant, but it's a rational function, not an affine function. And so it's not immediately obvious that it has an inverse Satake transform, but you can write this as a sum according to a formula often called Moyel's formula. I can write this as a sum over the symmetric powers of the irreducible representation sigma. And on each one of these, I'm dealing with a function which is affine and of compact support. And so I can look at that inverse transform. And the way it works out is that you can then just take the formal sum of all those individual terms and you get a function on the group itself. So the basic function is basically what I call the inverse Satake transform of the L function, is a rough way of putting it. It doesn't tell you much about it, but that's what it is. Now, however, in order to get exactly the basic function, there's a somewhat arbitrary, but not quite, normalization want to take place. You fix your S, you set it equal to lambda rho divided by 2, where rho is the sum of roots. And this is a standard delta to the 1/2 if you write it multiplicatively. And then you get the following expansion, again, following Molyneux's formula. And so you get the basic function, and yes, so now in the literature, most people who work with this assume that the center of the L group is actually isomorphic to C star. We've done that, but they put a restriction on the sigma for which the basic function is defined. They require that sigma on the center of G hat is just the identity map. I don't do that. It's not quite clear to me what role that restriction plays. It does simplify some things in some ways, but it makes things more complicated than others. So I assume only that the center, that sigma restricted to the central element, is just some positive power, a non-negative power of that central element. So if G is GL2 and I take sigma to be sigma 1, then each symmetric power of sigma is irreducible. And so as Tamagawa pointed out, that tells you almost immediately that the basic function is the sum of all the fmn's where n and n are integers and non-negative integers. And this is the characteristic function of the intersection of the matrix integers with GL2k. And in fact, the characteristic function of the matrix integers is a unique continuous function on the matrix algebra, which restricts to this function on GL2k. That's the general recipe which follows all examples of the basic functions. In general, things, meaning for representations other than the standard representation on C2, things are not quite so simple. Suppose that my sigma is the symmetric power representation on sk of C2. Then the character is what I write down there. And then I can write, in that case, the symmetric power necessarily has a decomposition into certain normalization powers of the determinant times sigma of km minus 2i. That's the generic way of writing it down. And there'll be some coefficients, delta kmi, which occur in that decomposition. And then I can write I add in my normalizing factor of the q to the km over 2, divided by 2 times the symmetric power. And I get a simple expression in terms of the delta function. And the basic theorem, which is very simple, very elementary actually in these circumstances, that the basic function is then derived immediately from the multiplicity, the decomposition multiplicities. And you get, automatically you get certain powers of Q which appear in that decomposition. So the basic idea is that once you have the decomposition of the symmetric space, the symmetric power at Sm, then you immediately get a formula for the basic function attached to that irreducible representation sigma. So as a check on calculations, which I've done many times, if you set Q equals 1, the basic functions just become the ordinary weight multiplicity. And that's very useful to know sometimes. So there are 3 functions which are very closely related. There's the weight multiplicity, which I call omega m. There's the decomposition multiplicities, which I call delta. And then there's the basic function itself. And all of these are very intimately related. There's something which plays a role, which becomes immediately apparent in all these calculations, is you're basically using constantly the fact that the weight space for the dual torus A hat is isomorphic to the co-root, the co-weight space for the torus itself. And so you're constantly transferring back and forth between functions on the weight space of the dual torus and functions on the torus itself. Sometimes this leads to paradoxes. So as I say, for GL2, computing the basic function reduces directly to computing the irreducible decomposition of symmetric powers. And as I also say, it's not true in general. The inverse Satake transform in general involves Cauchy-analytic polynomials. So the problem now is to find a formula for the decomposition multiplicities. Now, I should say, I'm not going to tell you very much about how to find that formula for the decomposition multiplicities. It's a classical formula. It goes back to almost unbelievable, actually. It goes back almost 170 years. It starts with Cauchy and goes to Sylvester and Cayley, and all the way up through the early 20th century, involvement. There's a huge literature on these decomposition multiplicities. But actually, we'll see. The final formula occurs like nothing else in representation theory as we know it. So I'll tell you a little bit about what the decomposition multiplicities are. The basic fact is they're just very complicated. So take G equals GL2 and sigma equals C2. I'm just going to show you one example. So the character of sigma in this case is, remember, U and V are the diagonal elements in the dual group. The character is U squared plus UV plus V squared. And the irreducible decomposition is that. And in this case, the irreducible decomposition of the symmetric algebra is rather simple. Pick a basis of C3 with respect to an eigenbasis with respect to the matrix T, 1 over T. And then tau times EI is T to the 2 minus 2I. It turns out that there's a sort of an obvious way to parameterize the weights, which are not usual in representation theory, but in this case, it turns out to be absolutely essential. And then you get an eigenbasis for the symmetric algebra at SM of sigma, and made up of products of the E0, E1, and E2, where the sum of the exponents is M, and you can calculate its tau weight, that is to say, the weight with respect to the element tau as 2M minus 2M1 plus 4M2. So it's 2M minus 2I, where I is equal to M1 plus Mi. So the weights with respect to tau are all of the form 2M minus 2I with respect to I in the interval 0 to 2M. And its multiplicity is a number of Mi, a number of M's with sigma, M equals M0 plus M1 plus M2. And the weight is M1 plus M2 equals I. You can draw a nice little picture of that. And this is one of the reasons I don't make the normalization in the literature that other people do. You can draw a little picture and you can do your calculations. And you can see that the weight multiplicities are given by some funny, slightly odd formula. The floating, this is the floor of the integral part of I over 2 plus 1, or 2M, the integral part of 2M minus I over 2 plus 1. So the basic idea, which repeats itself throughout the whole theory here, is that weight multiplicities are, they're calculated in certain ranges. And the formula in different ranges is rather simple and changes drastically from one range to the next. So here it's just 2 ranges, and that's very simple. In general, there'll be a large number of ranges, and the formula changes quite drastically as you go along. So the formula is very, very different in each of the ranges here, 0M and M to 2M. And so the span of the tau weights is all of the range 2I with minus L I to L. So you calculated the weight multiplicities of the representation, of the symmetric representations, but it turns out that there's a very simple relation that holds for all groups, which is a little bit different from this, but it tells you the decomposition multiplicities are given immediately in terms of the weight multiplicities. Namely, it's just the first difference. And so the functions delta and omega determine each other. And here I applied the formula we had for the omegas, and you get the delta is equal to the integral part of I divided by 2. So it alternates, it goes periodic like this, 1, 0, 1, 0, 1, 0, etc., until the range is exhausted. And the range will depend on M. The range will be 2M if I'm looking at the symmetric algebra of degree M. And so you derive immediately from this and the previous formula and relating the basic function to the decomposition multiplicities, that the basic function given at various points of diagonal matrices M0, M minus 1, 1, and so on, is given by 1, 1, 1 plus q squared, 1 plus q squared, 1 plus q squared plus q fourth, and so on. And there's a very simple formula for that. Now, in general, for arbitrary representations other than the sigma 2, it's much, much messier. What's really more messy about it is that the decomposition formulas are much, much messier. So the representation sigma 2 is the only simple case. The decomposition already of sigma 3 is, well, more interesting. what follows are the graphs of the multiplicity with which sigma 3m minus I occurs in the symmetric algebra of sigma 3. So these are the graphs. So it's a bar graph, and at distance I along the horizontal axis, you get the decomposition multiplicity. So it reaches a peak and then it decreases again, and that keeps on going. So it's a repeated pattern that the things are nicely out to 2 times m, and then they go down. And actually this continues. There's a nice formula relating sigma on either side of the central point here. So the sigma delta goes to negative values, and that's because the weight multiplicities reach a maximum at the right-hand point of this. So I haven't graphed the weight multiplicities. It's not very educational. But for example, this tells you that the symmetric power S of 10 of sigma 3 is equal to sigma 30 plus sigma 30 minus 4 plus sigma 30 minus 6, and so on. You can read out directly off what the decomposition is. And the behavior here is like the one for sigma 2. The behavior is distinctly different in different ranges. As I say, this is a pattern that repeats throughout the whole subject. In fact, in this case, you can guess a formula by just looking at the bar graph, and you can figure out that you set some A equals some array of length 6, and then the decomposition multiplicities are given directly in terms of that, in terms of values of A modulo 6. So you get sort of what's called a quasi-polynomial periodicity. So what this means is that there's a period, in this case 6, and in each element of a congruence class, modulo that period, modulo 6, you get a polynomial function of the decomposition multiplicity is given by a polynomial function. But still, so there's some quasi-periodicity, I guess you'd call it, or polynomial periodicity that describes things. And this again is general. This is a part of a very general theory of something called quasi-polynomial functions, which has a huge literature attached to it. Things get messy. Here's delta 4, for example. If I look at the sigma 4 and I look at its symmetric 20th, the symmetric 20th power, then the graph, the equivalent bar graph, looks like this, which is decidedly more bizarre. What happens, however, is not too bad. If I take m larger and larger and larger, and you can sort of see a pattern maybe approaching, as I get sigma m goes larger and larger and larger, then I get something which approximates a piecewise polynomial function. And that's, again, something which occurs in general. In fact, the formula for that the formula for the polynomial that you get is a formula due to the Joseph Sylvester, an American and English mathematician in the middle of the 19th century. Very peculiar fact. So as I say, these are what's called quasi-polynomial functions. And there's a very beautiful and general theorem due mainly to Bernd Sturmfeld, which gives you a sort of a general environment in which to look at such things. So I recall, to be precise, a quasi-polynomial function on a lattice is one that is a polynomial on each congruence class modulo some multiple of the lattice. And as I say, you have some nice asymptotically polynomial. Still, these functions, it's just not clear what these functions mean in representation theoretical terms. So I've seen what the graph looks like for a fixed m, but in fact, we can do a little better for different SM. They all fit together in a simple pattern too. So I've outlined here the rows together. So as before, if we go back to here, you can see that somehow there's some consistency of behavior as m increases. And I can put those all together in a different kind of picture. And now I can analyze this numerically. And what you get is a 6x6 periodicity in the left-hand side. There's also another 6x6 periodicity of some kind in the right-hand side. And each of these different pieces, the pink squares divide the areas where, divide the two ranges in which I behaves differently. So on the left-hand side, you can look at this very carefully. You'll see there's a very obvious pattern. On the right-hand side, it's a more interesting pattern. For example, if you translate on the right-hand side, if you translate up vertically by 4, a level 4, then it occurs exactly periodically. And as I go higher, and as you can see, I get, so m is the vertical height here, And as m increases, things expand out very nicely. Right. So in the previous image, we were plotting data associated to weights of the A hat on, that is to say, on X star A of hat. But if we apply the inverse Satake form, we wind up with a plot of the basic function on the co-weight space of A itself. So the way the function delta 3 behaves is mirrored in the way the basic function behaves, although in a more complicated way. So in the end, I don't have it yet. This is unfinished work to some extent. In the end, I think you get some sort of quasi-polynomial description of the basic function itself, but because of the powers of Q, it's a little more complicated. I think some ideas basically due to 19th century mathematicians give you the right way of formulating things. It's not so easy. So you might ask, well, what does this have to do with, with matrix algebra or in general other symmetric? So the answer is the replacement for the matrix algebra is something called a spherical embedding of the group GLN, or GL2 in our case. A spherical embedding the simplest example is just the matrix algebra. A spherical embedding of a split reductive group is an open embedding of G into a normal algebraic variety on which G cross GX compatibly with the action on G, and which is a finite union of B cross B orbits, where B is the Borel subgroup. The matrix algebra is an example of that. It's an elementary exercise to extend the Gaussian elimination to the matrix algebra. And the Windberg monoids are also spherical embeddings, which happen to be affine varieties. But in general, the matrix algebra in the theory that I'm presenting is replaced not by the monoid, but it's replaced by other spherical embeddings, which are a bit more complicated and which are in fact not affine varieties. It's not quite clear to me. So there's an extensive literature of work by Ngo and various people, very interesting work and certainly valuable, but they work only with the Windberg monoid. It's not clear to me at all how that relates to what I'm telling you today. Now, if G is an algebraic torus of spherical embedding is just a toric variety, and the spherical embeddings are based on the construction of the spherical embeddings we are interested in, the ones generalizing the matrix algebra, are based on certain toric varieties. I'm not going to tell you very much about spherical varieties, except that the spherical embeddings we're interested in are essentially parametrized by toric varieties, which are invariant under the Weil group. So if I have a reductive group G and then I have a maximal split torus A, the spherical embeddings of G that we're interested in are those which are associated to toric varieties, which have an action of the Weil group on them. And the literature on this is not so clear. There are bits and pieces which are clear, but it's very hard to derive exactly what you need from the literature, but it's possible. So for example, if I take G equals GLN, and the toric embedding is that of the multiplicative group, the multiplicative torus of degree n into affine space, then what I recover is the matrix algebra. But in general, you get much more interesting examples. So I'll show you some pictures. Yes, so as I say, the toric varieties are parametrized by certain complexes of cones, which are assembling of cones together. And so, for example, for GL2, you get the following complexes of simplicial cones, which is very simple. So the figure on the left here is for sigma 1, that's the standard representation. The one in the middle is sigma 2 and sigma 3. So in general, if I'm looking at sigma k, the k symmetric power is a representation of GL2c, then I get associated to this a toric variety associated to an assembly of k symmetric cones, k homogeneous cones. And so what's interesting is, so what are these toric varieties? Well, these toric varieties are really sort of semi-compactifications of the torus. So what happens, each one of these cones describes an asymptotic behavior. If you're not familiar with this, it takes a little while to get used to it. But for example, each one of the cones in these pictures represents a point at infinity. So for example, if I look at the left-hand one where I'm looking at sigma 1, then the point at infinity is just the zero matrix, the null matrix. If I look at the one in the middle, then I get two cones, but these are no longer points. These are now turned out to be orbits of G, but they're not trivial orbits of G. They're actually a variety. They're curves, and that's also true of the other one on the left. So you get a rather complicated structure. First of all, complicated because of the toric variety, but that's actually relatively simple. But then you get rather more complicated varieties, which are related to parabolic varieties attached to the group. So there's still some things I have to work out, which are probably not too hard, but I just haven't had the time to do it. But it's not too complicated. And the basic point is there's a Schwartz space attached to these as well, which is, it's hard to describe. So I'll just summarize what I'm saying is by saying that basically the Schwartz space, once you have the basic function, the Schwartz space is obtained from the basic function by chopping it up and transforming it in all different kinds of ways. And so in order to understand what the Schwartz space of that replaces the matrix algebra is, in order to understand that, you have to understand the basic function very well. And then you just start chopping it up and moving it around. And that gives you the Schwartz space in general. That's easy to see that that's what happens in the case of M2K. That you get the Schwartz space of locally constant functions on the matrix algebra just by chopping up the basic function and moving it around. This is not my invention, but what is true, and does seem to be my own observation, is that in general, quasi-polynomial functions on a cone of a toric variety is somehow always related to some sheaf on a symmetric space on the spherical embedding. Okay, so as I say, this is a standard construction. I don't know who first introduced it, but it's already mentioned in the original paper by Braverman and Kazhdan. So they talk about constructing Schwartz functions in terms of the basic function, but as I say, they don't know what the basic function is. So it's a very interesting question. So once you have the basic function, you derive from this a sheaf on some spherical embedding, and the sheaf has stalks. The stalks are very interesting. They are what the theory of quasi-polynomials tells you without too much trouble is that the stalks are themselves finitely generated modules over Q, the variable Q. To explicitly compute them is not too hard. I have many examples, but I don't have a general theory. But even then, already, even the few examples I have leaves open the question: what is their significance? What is it? What can these complicated quasi-periodic functions possibly have to do with representation theory? And the answer is I have no idea. However, there is one fact, which is which I've mentioned before, is that there's an asymptotic behavior. In all cases, as you let m go to infinity, then there's a formula due to Sylvester that tells you, and my main theorem, which I haven't stated yet, which tells you that asymptotically things behave very nicely, even though at finite levels they behave very oddly. So I'll tell you the formula, although it won't mean anything to you. I just want it on the record, so to speak. The theory that's due to Sylvester and Cauchy and Cayley is something called the theory of denumerants. So if I take an array of positive integers, the associated denumerant is a series that you derive from a very simple expression, 1 minus x to the a, for a equal to the various a's. And what the theorem due to Cauchy is that, in fact, this is a quasi-polynomial. That is to say, it's periodic. It's a polynomial function on various congruence classes. It's an amazing fact that it's still somewhat a useful fact. There's a recent large literature on denumerants and related quasi-polynomial functions, and they're probably relevant to the theory that we're proposing here. So what's important is, for the final formula I express is, since they're periodic, they can extend it to all integers, not just the positive ones. So the dA is written out as a series, and a power series in x, and you get coefficients, and that's the denumerant function. But actually, because of Cauchy's theorem, this extends to all negative values of n as well. And that turns out to be an extremely important fact. And there's a very beautiful theorem due to Earhart called Earhart reciprocity, which tells you how that works. It's an extremely beautiful part of the theory. it would be nice to know positively that this is all relevant to representation theory, but I don't know that yet. Anyway, the formula is this: I attach denumerancts. So the denumerancts are defined in terms of certain arrays of A's, and I get K A's. I get K of those K of different arrays, and for each one of them, I get a different denumerant. And the formula for the weight multiplicities involves the denumerants in different ranges. And so this gives you a quasi-monomial in each one of the ranges that Sturm-Feld's theorem tells you about. It's not easy to comprehend, as I say. But as I say, it was Joseph Sylvester, who found an asymptotic expression as m goes to infinity, so to speak. Then I get actually it's a locally polynomial in each one of the ranges. And that's an extremely beautiful fact. Again, it's a very deep fact, actually. And I suspect that if this theory has any global application whatsoever, it will be because you know these asymptotic expansions. So following a remark of Yannis's, you'd like to be able to plug basic functions into the trace formula. There's no obvious way to do that, but almost certainly if you are able to do that, it will be because you will know the asymptotic expression that you get from Sylvester's formula. Okay, for higher rank, things are considerably more complicated. One problem involved is that the inverse of the Satake transform is more complicated. It involves these casualistic polynomials. I have some ideas about how to deal with that, and it's rather interesting, actually. But still, this means that the computation of basic functions for higher rank groups doesn't factor into the two steps, finding symmetric multiplicities and then applying the Satake inverse. There is a formula due to Wenwei Li, which somehow combines those two steps into one formula and allows you to find asymptotic formulas in general, but it's not quite clear to me that that's actually all that valuable. It's just not clear how to use Wenwei Li's result. Other bad news, however, is more interesting. In general, we've seen that the behavior of the decomposition multiplicities and the weight multiplicities goes by a small number of ranges, which is proportional to the dimension of the representation, sigma. But in general, you get something much more complicated. So if I look at GL3 already, it's very complicated. If I look at, so here, what I'm looking at are slices of the regions we had for GL2. We're looking at horizontal slices. And so what happens is, if I take the shaded area here represents the dominant weights, and each one of these has a dominant weight. Each one of these diagrams has a dominant weight, so it corresponds to a representation of GL3. And so how do you get the regions which correspond to the regions we had for GL2? Is you look at all linear, you take the highest weight, you look at its Weyl, the convex hull of the Weyl orbit of the highest weight, and then you draw all possible lines in between. And each one of the regions you get, so the complement of the lines you draw is a Sturm-Feld's region. So in each one of those regions, the decomposition multiplicities and the weight multiplicities behave very nicely according to a polynomial function. Well, for low dimensional representations, that's not too bad, as you see in the figure on the left. But already for just slightly higher representations, you get a horribly complicated structure. And it's actually, I would say, a challenge. You look at that, and my first reaction was yuck, but the more I look at it, the more I think it's possible to make some sense out of it. But it's not, obviously, that's a real challenge, in fact. Still, if you want to generalize my main theorem, then you have to understand what that decomposition is. So that's an interesting fact. So how do you parameterize the open orbit, the complement, the little chambers that you get on the right-hand side? Well, it actually turns out to be a classical problem in geometric combinatorics. A lot of textbooks and papers from the mid-20th century discuss that. But the answer is they don't know. There's no people, many people have tried to find a formula for figuring out how many chambers, they're called chambers, those open areas, and to figure out how you get chambers from the initial construction, but there's no universal answer. As I say, I have an idea, but I am not optimistic about that. So, as I say, another open question is there any structural significance to the stalks of the L sheaves? And the answer is, I don't know, but I suspect so. What's tempting is that the formulas you get are rather similar to the formulas you get for the asymptotic behavior of matrix coefficients. It seems ridiculous at first, but in fact, it's the way. So the asymptotic behavior of matrix coefficients is governed by something called the wonderful compactification of G cross G acting on G. And that's somewhat similar to what I have here. But it's that for the matrix coefficient question, you have the Jacquet module, which controls the asymptotic behavior, and the so-called canonical pairing of Jacquet modules. It's not so clear that there's anything like that here, but I would not be surprised. I would expect, in fact, something to arise, which is interesting. So I think there's some algebraic significance. Most in question, another interesting question, which might be answerable without too much trouble, is GL2R and GL2C. There are formulas, well, there are statements, not formulas, there are statements due to Go and Lowell about this in a recent paper, but they don't tell you very much. What's tempting is that the basic function in Godemont-Jacquet is an exponential, has an exponentially decreasing function, a kind of normal distribution. In general, what I expect to be happened is you get, it seems impossible to imagine, but I think you get some kind of diffusion initiated at the smallest G orbits on the spherical embedding. I don't see any other possibility. That explains, in a sense, what happens for GL2 and the standard representation. The big question, which I have no idea at all, is what do you do for global? Is there any possible global application? I have no idea, really, but nonetheless, I say there's some hint that this is vaguely related to Langland's work on beyond endoscopy. The basic function occurs implicitly in Malor's talk, but it's never really been taken up very carefully. It's not quite clear how this will behave in general. Right, Langland's himself toys around with this idea. Langland's actually mentions the question of symmetric power decompositions in his paper on singularité et transfert, but it's one of the few cases where he doesn't actually get very far. He is able only to deal with sigma 2 for reasons because that's a very elementary case. This also appears implicitly in autoexesis and in Malor's work, but there's no systematic attempt to introduce it. I noticed that Yannis introduced the basic function in his talk. It's not quite clear to me the relationship between his basic functions and these basic functions. And here are some references, but I can skip over them. I'm through. Hello?
Yes. Thank you. Very nice talk.